Now, talking about wireless networking, we need to think about security a little bit now that we have a little bit of background. So we have three technologies that we use in 802.11, and they do provide some backwards compatibility. It's direct sequence spread spectrum, DSSS, frequency hopping spread spectrum, FHSS, and orthogonal frequency division multiplexing, OFDM. Now, I know those sound like a mouthful, but this is how wireless networking works. So let's look at DSSS first, the direct sequence spread spectrum. Now, this is a wireless technology that spreads a transmission over a much larger frequency band and with corresponding smaller amplitude. So by spreading the signal over a wider band, the signal is going to be less susceptible to interference at a specific frequency. So this was one of the first standards they came out with, was the DSSS. And then they developed the frequency hopping spread spectrum. Now this wireless technology spreads its signal over rapidly changing frequencies. So the frequencies are changing and we're bouncing from frequency to frequency. Now each available frequency band is going to be subdivided, or can be subdivided, into sub-frequencies below that. So the signals rapidly hop, bouncing among these sub-frequencies in an order that is agreed upon between the sender and the receiver beforehand. So they're on the same page, right? If I'm hopping frequencies and you don't know where my next hop is, we can't communicate. So we have to negotiate that at the beginning. So the benefit of FHSS is that the interference at a specific frequency will affect the signal during a short interval, because there may be interference here, but I'm getting ready to hop down here, and so we're good to go. So I may just hop right around that interference. So it's working on the probability that it's hopping so much that there won't be interference there. And then the orthogonal frequency division multiplexing. Now, this means a signal is subdivided again into sub-frequency bands, and each of these bands is manipulated so that they can be broadcasted together without interfering each other. This gives us higher throughput. Now, in an OFDM system, each tone is considered to be independent, orthogonal, to the adjacent tones, and therefore does not require any of those guard bands that we may have in our frequency ranges. So this is the latest and greatest, if you will, of the standards that we have. 802.11n supports the orthogonal frequency division multiplexing because we get higher throughputs that way. That's how they say we can get up to 300 to 600 megabits a second. Now we know we have the 2.4 channels and we have the 5 gigahertz channel. Remember, they're not backwards compatible. All right, so we're on the 2.4, we have to talk 2.4. If we're on the 5, we have to talk 5. Now, we didn't talk about antenna types yet, and there's a couple that I want you to be familiar with. One of them being omnidirectional. Omnidirectional antennas is probably what you have in your house. I can't be for certain because I don't know everybody that's watching this video, but it's what I have in my house, right? It goes out every direction. It's kind of like if you took a rock and you threw it in the water, right? The ripples, they go out from the center in every direction equally, right? One of them doesn't go faster than the other one unless there's something there stopping it, which we could very well have in our wireless networking as well. But for the most part, they ripple out from the center. And that's what an omnidirectional antenna does. It's always sending it out, kind of like a starburst, out into the air. And our devices will see that traffic or understand that traffic. Now, we usually put omnidirectional in a central location because of the way that it behaves, right? It comes out in every direction equally. If I was to stick it in the corner of the office building, it would still work, but now some of that signal might be going outside on the sidewalk, may bleed to the next building, may bleed to the next house. So they're seeing our signals now. That could be a security issue. I don't want people seeing my wireless traffic. Wireless is inherently insecure anyway, right? So everybody says. So if they're seeing my radio frequency signals over there, that may be bad for me. I need to either turn the power down Or take my access point that's running an omnidirectional antenna and put it in a more centralized location. And then I have equal access throughout the building. Now, let's say I have to put it over here. You know, our infrastructure, the logistics, there's no way to get around it. I have to have an access point right here. I want to use like a directional antenna. Be like, okay, that's fine. We have to put it here, but I want to make the signal go this way. I don't need it going outside. That's wasting power. That's wasting resources, and that's introducing a vulnerability that we just don't need or want. So we can put a directional antenna and say the wall's here. We have to put the access point this way. We'll put the directional antenna facing inwards. So now the signal is staying inside of the office or inside of your organization. We also have some authentication and encryption when it comes to wireless. Now, first one I want to talk about is WEP, W-E-P, Wired Equivalent Privacy, or you may see it as Wired Equivalency Protection. Now, this is a pretty weak authentication mechanism. It's been cracked. It's the keys. It has 64-bit or 128-bit keys, and it runs an RC4 algorithm. And the reason that it is weak is that the keys never change. Once the key is established, it doesn't change at all. So once a client or a device accesses the WEP access point, they establish the key. And after a while, you can see a pattern. If you were to sniff the wireless traffic, you could see the communication stream between the device and the wireless access point, and eventually you would collect enough information where you could actually crack the key within seconds. There are devices out there and software out there that will do this. So we don't want to use WEP if at all possible. I guess it's better than nothing if that's all you can do, but I don't know why that would be all you can do anymore, because I don't even know if you can purchase an access point that will only do WEP or even has the capabilities of doing that. So that one's kind of old. We have WPA, Wi-Fi Protected Access. Now this has a 128-bit key, but it's a little better than WEP because this runs something called TKIP, Temporal Key Integrity Protocol. It changes the keys about every 10,000 packet or so. So you're going to see a pattern for a little bit, but then the pattern is going to change, so you got to start over. And then you see it, and then the pattern changed, and you got to start over, right? So that has TKIP, T-K-I-P, built in. It also has Extensible Authentication Protocol. This is for our authentication. WEP doesn't have that. There's two different flavors of EAP that we can run. One of them is LEAP, and one of them is PEEP, Lightweight Extensible Authentication Protocol, and Protected Extensible Authentication Protocol. Now, when it comes to WPA and WPA2, which we haven't talked about just yet, there's a couple different ways we can implement this. We could do WPA personal, which means we have a pre-shared key. A lot of people at home, I've seen a lot of small offices and home offices do the exact same thing, but they have a pre-shared key. Again, you go get your wireless access point from the department store, you bring it back to the office, you plug it in, you start configuring it, right? Inside there, you have to put a key, right? You put the passphrase, the password is the key. So what they can do, or what they will do, is put that in there and then share it among employees or your family members, right? You tell your spouse, you'll put it on your kids' devices or whatever, so they can access the wireless. Because without that pre-shared key, they can't access it unless they crack your key somehow. So that's WPA personal. Now we can have WPA enterprise as well. This uses a different mechanism, and this uses an authentication server, like Radius, for example. You can have a Radius server for authentication. So when you have individuals come into your enterprise or your organization, they may try to access the wireless access point to get internet connectivity. as soon as they do that, they're going to have to authenticate themselves. Do they have a username and password to get on the wireless? So we don't have that whole pre-shared key thing. Now they have to see if they have an access account or a domain account or some type of an account somewhere for authentication that this radius server can find and say, okay, that's your username and password, looks good, come on the network. Now, we also have WPA2, and this is what you want to do if you need to support wireless. Now, WPA2 is stronger than WPA. It has 128-bit, 192-bit, or 256-bit encryption. This guy uses AES, the Advanced Encryption Standard. It also uses CCMP, which is counter mode with cipher block chaining message authentication code protocol. I know it sounds like a mouthful too, but it makes us more secure. This is where they were trying to get when they developed WPA, by the way. They wanted to get to where WPA2 is, but they couldn't. They couldn't get there fast enough. They knew WEP was broke, they knew it was unsecure, and they needed a solution quickly. So that's where WPA came in to fix that with the temporal keys. And then they got stronger encryption, stronger protection with WPA2. Now in WPA2, we can run personal, again with the pre-shared key, and we can also do the enterprise level stuff like with our radius server with those authentication servers. So that's not just a WPA thing, it's WPA or WPA2. Now, when it comes to our wireless networks, we need to secure them down. I know everybody gives security top priority when it comes to wireless, right? Not so much. They need to, you know. People don't think about some of this stuff in their homes. I've had multiple discussions with friends and colleagues about, you know, the very first thing, changing the default configuration. They go to the department store, they buy a wireless access point, they bring it home, they plug in the power, they plug in the Ethernet cable with the RJ45 connector, they plug the other end into their modem or router they got from their ISP, and they're done, right? They know, they see, oh, well, there's my device. That's the one I just bought. It's the best signal strength. That's got to be me. So they'll connect to it in their operating system, and they're up and running. They're on the internet, and they are happy. But they are not secure whatsoever because they left that default config on there, right? If I drive around, walk around, sometimes I don't even have to. Like we said earlier, antennas strength is strong nowadays. I may be in the next building, in the neighborhood with you. You may be in the house next door, and I see your access point, and it's unsecure. All right? If I see it's a certain brand, all I have to do is do a quick internet search for default passwords for a certain brand. I get my list. I try to open up your admin console, and I use that list of default passwords that I found, and I'm going to get into your router. Don't allow that to happen to you, and really don't let it allow that to happen to your organization. Change the default setting. Get in and change the administrative password. Put a good, strong passphrase on there. 14, 15, 16 characters. Make it complex. There's no reason people need to be getting in there other than the people that need access. Your service set identifier. It's usually the first thing people say. Well, change your SID, your SSID, right? Change the name of it. Don't leave it as the vendor underscore and a couple numbers or something like that. And most people do that one sometimes. It depends on how diligent they want to be. If they, in my previous example, if they just go to the store, buy it, plug it in, and run with it, the SID's going to be the default. And that's even worse. So change the SID. Change it to something meaningful. Maybe your last name or your neighborhood or something that means something to you. I've seen lots of clever ones before. I can see them in my neighborhood. I live in a pretty congested neighborhood. One of them says FBI van number 2. So I'm pretty sure it's not an FBI van, but it very well could be, I guess. I'm thinking it's just somebody being clever with their access point, naming it for that service set identifier. We could use MAC address filtering. Now, this is a pretty good layer of defense when it comes to wireless access points, though it's a little bit of an administrative headache. And what I mean is, what we have to do is look at every device that is supposed to be on our network. Now, every device we know has a network interface card, a NIC, and on that NIC, we have a MAC address. Remember those layer 2 addresses we talked about. So what you can do is get you a list of the MAC addresses of all the devices that are supposed to be on your network. You're going to go into your router configuration, your wireless router configuration, your admin, portal. It's usually a web page nowadays. And you can go to the MAC filtering tab or the section where you can put in MAC filtering. And usually they have 2 places. Allow all of these but not these, or deny all of these but only allow these. So you might pick deny everything, deny every MAC address except for the ones that you explicitly put inside of the router. So you're going to take that list of all the devices that you've written down and start typing them in to the wireless access point. So now during the negotiation, even if I know the pre-shared key, once I get authorized and authenticated, it's going to look at my MAC address and say, no, you don't have access. You're associated with me because you know the pre-shared key, but you're not going to be authorized because your MAC address is not going to be authenticated. You're not in the list of go, no go. Think about antenna placement and power levels. We talked about that just a second ago a little bit. We don't want to put an omnidirectional antenna with full power at the edge of your building. There's no reason to do that. You're allowing your signal to leave your perimeter, to leave, maybe to become attacked, sniffed, hacked. That is a vulnerability. You're increasing your risk to your infrastructure when you do that. Again, if there's no way around it, right? Directional antennas are great because they direct which way the signal needs to go. Sometimes you go by these wireless routers and you may get an enterprise level router, or some of them you can get at the department stores nowadays are pretty powerful. You may put it in the center of your building, center of your house, and it still reaches outside. You can go 2 houses down in your neighborhood and look at your phone or mobile device and be like, I'm still seeing my access point. Well, the power's turned up too much. It's not going to slow your network down. It's not going to make things run worse if you turn down the gain on your antenna. It's just saying don't broadcast out as much, not as powerful, right? You're not a radio station. It's working off radio waves, but you're not trying to broadcast to everybody in the neighborhood. Turn that down a little bit. Bring that signal in. Try to keep it as close as you can without losing connectivity. You don't want to leave the people out in the corner offices. If you turn it down too much, it may not reach them very well. They may have some latency or intermittent issues. So you can't turn it all the way down, but turn it down a little bit and then maybe do a site survey. Like, oh, well, we're still reaching 15 feet outside of the building here. Turn it down a little bit more. Okay, we're getting closer to the perimeter now. Can the corner offices reach? Does everybody still have connectivity that needs it? All right, so you have to think about that stuff when it comes to securing your wireless networks, because you don't want that signal leaving the building like that. You may have a captive portal. So you get on the wireless access point, all right? Maybe it has authentication, maybe not. Sometimes it's open, has open authentication, but it still redirects you to this portal. And this portal might say, this is free Wi-Fi. Do you agree to our terms of service and the terms of usage? Right? I see this a lot in hotels. Right? I sit down, I connect to a hotel Wi-Fi, I open up a browser and it redirects me to their portal. And sometimes I can pay for the faster internet or I can get the free internet, and then I have to agree to their terms. I won't use their network for hacking, and I'm not going to do malicious intent. I won't break the law and things like that. Airports, the same way, right? You'll log on to an airport Wi-Fi. You open up a browser and you're taken to a portal page. And you're going to see their terms, right? Their agreement. I agree not to do bad stuff. I'm paraphrasing. You check I agree and you hit submit or OK or whatever button they have, and they allow you to get onto their wireless access point. We want to encrypt our wireless traffic. Try to encrypt our traffic as much as we can, because there's no mechanism in the air to say, travel just this way, nobody sniff my traffic, right? It's not like it's running in a cable along, in the wall, where if somebody wants to intercept that traffic, they have to get a hold of that cable. They have to get to the other end or your end or tap the cable somehow. Wireless is just out there. It's just floating around, so anybody can grab it. Again, if your traffic is encrypted, it shouldn't matter. It may make you feel uneasy, but if they do sniff some traffic, they do capture some traffic, if it's encrypted, and it's encrypted somewhat well enough, they're not going to be able to see what the data means. They will see something, but they're not going to understand it because they don't have the key to unlock the encryption. So that's a very good level of defense for us for securing our wireless networks. We may use VPN solutions. This is what I like to do when I'm at the airports, right? If I have to get online and I have to do something that requires me to type in any credentials, I will log on to their access point, but then open up a VPN connection to a trusted network, say back to my house. So now any traffic that is being passed is going through my tunnel, and whoever else is on the wireless network shouldn't be able to see that information. So if I have to, jump on and check a critical email or check the bank account for some reason real quick, right? Something that I don't really feel comfortable doing on an open public wireless network, I'll set up a VPN tunnel and get to a trusted network. And I pretty much trust my network at home. It's still a wireless network, yes. It is in a neighborhood, yes. But it's my network, so I feel pretty good about that. We have vulnerabilities in wireless as well. Just like we have vulnerabilities in a wired network. Well, maybe more in a wireless network. I don't know. It depends on how you want to look at it. We could have data emanation, right? Is leaking out there. That's not good. Jamming or interference. Somebody could be interfering with your signal. They may be doing it unintentionally. If you have a next door neighbor, which a lot of us do, right? I don't know if you live in a neighborhood or subdivision of some sort, but those houses are usually fairly close, 20 feet apart, 25 feet tops. They have an access point, you have an access point, they have everybody in the neighborhood seems to have wireless nowadays, right? I can open up my laptop in my home office and see about 25 different access points just from my home office. And that's not walking outside. I'm not turning up the antenna. I'm not using any external antenna or anything like that. So I know there's all kind of people around there. Well, there's only so many channels that we can play around with before they start interfering with each other. Now, for the most part, you can leave your access point on auto. Let it auto negotiate which channel it needs, because it's constantly seeing what's around, and it will negotiate that as far as if they're using channel 6 next door over here, I'm going to use 1 because I don't want to overlap those channels as best I can. That eliminates or lowers the interference that we could have with each other. And hopefully theirs is on auto negotiate as well. And that way all these access points are always talking and they're negotiating with each other on which channel they're going to use. They're going to see that that's using that channel, they're using that channel, so I'm going to say, well, okay, I can see what they're using, I'm going to use something different. Packet sniffing. I've mentioned this many times already. The data is just out there. It's just in the air. What prevents us, or what prevents an attacker from just holding up an antenna and capturing that traffic? Do they even have to hold it up? They could sit on the floor. If your signal strength is high enough, they could sit outside in their car. Packet sniffing is bad. I don't know how else to put it. For a lack of a technical term for you, we don't want people sniffing our traffic. That is our traffic. That's private information. That's what we want to do, the encryption like I was talking about. Because sniffing wireless traffic is so easy. It's not like you're tapping into a wire because it's just out there. So it's easy to obtain. War driving and war chalking. It's not really a vulnerability, but I put it here because it could be a problem. If you have people that are looking for open Wi-Fi, they're driving around, they're just looking for the open access points to do, more than likely, malicious activities. If I was wanting to do something malicious and I don't want to get caught, I could go do it from your house, your access point, because it's unsecured. And now if something happens, where is it going to point to? It's not going to point to me. It's going to point back to your IP address because I use your router to conduct my attack. Because you left the default configuration there, I got into your router and I did whatever I wanted to do. So that's why we have to get in there and change that default configuration as well. Now, war chalking is war driving, and then once I find something, I can mark that territory for somebody else later. Maybe somebody else in your group or clan, faction, whatever you want to call them, right? Of little hackers or attackers. And you can say, well, this one's open. So you can literally draw chalk on, say, a sidewalk or on a brick wall, concrete wall, so people know when the next person comes in, they know what's open, or if it's locked, or if it's how it's encrypted, or anything like that. SID broadcasting, turn that off. Again, that's like the first 1.5. Not the first thing you're going to do, because remember, we're going to change our SID, and then we want to uncheck that box that says broadcast the SID. Now, this is not going to stop your attacks. This is not going to be the be-all, end-all to nobody attacking your wireless access point, because there are tools out there, software tools, that can resolve your SID even if you're not broadcasting it. So this is not, again, the end-all to your security. It's just a security by obscurity, really. You're just don't give them, make them work for a little bit anyway. WPS and replay attacks. The WPS is that little number on the bottom of your router that you may see. So instead of having a pre-shared key where you have to get in and configure the router, now when you connect to it, you can associate with the router, and it's going to ask you for that WPS number. All right, that passcode that's on the bottom, 10-digit number that's down there, and you type it into the computer, and then it will negotiate and let you in. Now, if we steal traffic, I can do a replay attack. If I was sniffing your traffic and I saw your session ID, for example, I may be able to replay that information and pretend now I'm you. And the distant end computer is not going to know any different. Bluejacking and blue snarfing. It's kind of getting away from Wi-Fi, but this is our personal area networks. Now, we can have Bluetooth. You've probably heard that, right? We had the Bluetooth earpieces, the earphones, Bluetooth keyboards and mice. You have Bluetooth in your vehicle now, right? You can hook up your phone to the Bluetooth in the vehicle, and it will pull in your contacts. You can make phone calls inside the car. It will pull over your radio, your music, whatever you have on there, and you can play it right inside the car. But a couple vulnerabilities we have in the Bluetooth wireless is bluejacking and blue snarfing. All right, so bluejacking is unwanted messages, right? Unsolicited messages that you're going to be receiving or could be receiving. If you have your Bluetooth on all the time and you don't have it connected up to something, it's possible to get this spam. Now, blue snarfing is you're losing data. Somebody has attacked your device using Bluetooth and is actually pulling data off of your system. Rogue access point and evil twins. Used to find these quite a bit in an old job, but a rogue access point is somebody went and bought an access point, or they had an extra one laying around. I know I have like 4 or 5 at my house, where they can take that access point, take it to your organization or outside of your organization, your company, your building, your house, wherever you do business, give it power somehow, and plug it into your network. Public areas, like public libraries, for example, right? You could take an access point. You got a backpack. Everybody carries backpacks nowadays. You take your backpack, you have it in your backpack. You go find a quiet little corner with some power. You plug in your access point. You found a port, so you plug it into the port. You plug it into your access point, and you kind of hide it away. That's a rogue access point, because now I have wireless connectivity to your infrastructure. That could be a vulnerability, because now I'm taking your infrastructure and I'm kind of broadcasting it out to everybody. So depending on where I'm broadcasting it out to, I may be able to sit outside now and attack your network. I got in once, but now the radio signals are leaving the building and I'm getting that information. Now, an evil twin is still a rogue access point, but it takes it one step further. What I'm trying to do, or what an attacker is trying to do with an evil twin, is look like the legitimate infrastructure. So I could go, say, to a popular coffee shop that they offer wireless connectivity while you sit and enjoy your coffee and a pastry or whatever. So you can have a device, and I have a device that's actually battery operated. I could put that in my backpack. It has antennas, and I could name it. I can make that SID, remember that identifier, the same thing as the coffee shop. Then I could run an attack and disassociate everybody from the legitimate access point. Once that happens, their computers more than likely are going to try to reassociate with an access point. Now, though, they're going to attach to me because I look like the legitimate access point. So now the traffic is coming to my access point that's sitting in my backpack. I'm sniffing the traffic on my laptop because I'm just sitting there enjoying my coffee too. All the while, I'm moving on your data to a legitimate network. So you don't ever know the difference now. You're wirelessly going along, but everything's passing through me, through my access point, which is an evil twin. The twin part is we have identical SIDs, those security identifiers, or service set identifiers. So that's what makes it evil. And the twin part is I look just like the legitimate one. We could have weak encryption and have IV attacks. So we don't want to use weakening like WEP, the WEP. We don't want to use that type of encryption, right? An IV attack is the initialization vector attack. And that's exactly what we use for WEP. You collect enough of those initialization vectors, that's what you see to look for the pattern. Once you collect enough, there are tools that you can use that you collect the IVs, they look for the pattern, and they can crack your keys with weak encryption very quickly, with less than a minute. So don't use weak encryption if at all possible. That's the only thing you have available. I guess you could go ahead and use that. That may point you out more as a target than if you just had open network, but if that's all you have, something's better than nothing, right?